is the Leibniz rule for differentiation under the integral sign. So we have the formula of the Leibniz rule here. This is the one. So we have to first I have to first give an example, numerical example. So, for example, here this is a formula that we are going to use, the Leibniz rule for differentiation under the integral sign. So let f of x of t. So this is our function xt. Then a of x equal to x, b of x equal to x squared. So the function is I of x is equal to the integral of xt from x to x squared. Compute the left side directly. So we have I of x. Given function here is xt. So x to x squared. Take x as constant during integrations. So I of x is the integral of t dt from x to x squared. So this is equal to x to the fifth minus x cubed over 2. Then differentiate here. Differentiate the I of x with respect to x. So we have 1/2 of x to the fourth minus 2x squared. Compute the right side using the Leibniz rule here. So the partial of f with respect to x is equal to t from here. So partial of x with respect to t here is equal to t. Then from x to x squared, the integral is from x to x squared of t dt. So the answer here is x to the fourth minus x squared all over 2. And we have the boundary here. F of the upper limit here, f of x squared times x squared. So by using this part here, derivative of b with respect to x and derivative of a with respect to x here. And we have f of x bx here. So we have f of x squared, so derivative of x squared with respect to x. So x times x squared here, xt, and derivative of x squared equal to 2x. That is 2x to the fourth. And for the lower limit here, so xt here x is equal to x is equal to t. Derivative of x with respect to x is equal to 1. So this is equal to x squared. So combine everything here. So we have everything is we combine everything 5x to the fourth minus 3x squared over 2. So we have the final result here, match here. So the left hand direct differentiation is 1/2 of 5x squared, 5x to the fourth minus 3x squared. And the right hand here is also equal to 5x to the fourth minus 3x squared over 2. So they agree exactly. So interpretation, very important. So the integral term accounts for explicit x dependence in f of xt. The boundary terms correct for moving limits. This rule is essential in PDE of partial differential equations, variational calculus, fluid mechanics, control theory, and Navier-Stokes derivations. So we have the proof of this rule. The statement of proof is this one. But we have the given here, I of x equal to the integral of f of x dt. So we have the given f here, given functions. The integral of that from a of x to b of x, where f and partial of f with respect to x are continuous and e of x and b of x are differentiable. So this is what we want to prove, this one. All right, so step 1, reduce to fixed limits, idea, where the integral as a difference. So the integral from c to bx, f of x t minus times dt minus c integral from c to e of x f of x t dt, where c is a constant. So this avoid moving limits temporarily. So differentiate the first term here, f of x equal to c p of x. So c of p of x and f of x dt. So differentiate using the definition of derivative. So derivative of f with respect to x. So 1 over h. So the integral of f x plus h t dt from c to b of x plus h minus the integral of f of x t from c to b of x. So add and subtract c to bx and of the function f of x plus ht. So we have here, have to subtract. Then take the limit term by term. So the first integral here, we have the partial of f with respect to x dt by continuity of partial of f with respect to x. So the second integral, moving boundary for small h, the integral from b of x to b of x plus h. So approximately this is, so we can consider this a small area. This is equal to approximately equal to f of x b times b of x plus h minus b of x. Then take the limits as h approaches 0. So this becomes f of x bx times b prime. So let's combine here derivative of this f of x t dt is equal to the partial of f with respect to x from c to b of x plus f of x dx b prime. Then similarly, we can also do this for the c to e of x. We can use a similar uh, formula here. So this is where we have. So this first term, and we can consider this first term, and we have the second term here. So that is what we do here. So the final result here. So we have let's combine this. If we consider this the area, let's combine this. This is equal to a of x to b of x. So this is equal to the partial of f with respect to x from a of x to b of x. Then plus this one. So we have the final result here. So this is the final result. So why this formula matters? So this is a core tool in PDE derivation, essential in continuous mechanics, used in Navier-Stokes variational calculus control theory. Used in Navier-Stokes variational calculus, explain how moving boundaries contribute to change. This formula is the rigorous bridge between analysis and physics. So we have another example here. F of x t equal to x squared t cubed, e of t sine t, b of t t squared. Then we have I of t, the integral of f of x t from a to b, where a and b here are functions of t. So we have the integral of x squared t cubed dx from sine t to t squared. So by Leibniz rule, we use this formula. So compute for the b of t squared. So our f of t squared t equal to t squared times t cubed. So our x here is equal to x squared. So f of xt equal to x squared times t cubed. So that's the reason why this is equal to t cubed, x squared. So t squared here is equal to x squared. So x squared equal to t squared. So this is squared. So this is t to the fourth times t cubed times t to the 7. So compute for b prime t. B prime t is equal to 2t. And our e of t is function, or e as a function of t is sine t. Then the t prime, e prime here is, we have f of at. So we have uh, x is equal to sine t, so that is squared, and times t cube here, so t cube times t squared. So compute for e prime t. So e prime t is cosine t. Compute for the partial of f with respect to t. So that is equal to 3 squared t. compute the integral term. So the integral term here is equal to t to the 8 minus t squared sine t cubed. So combine all terms. So combine all terms here. So it is 7 we have here. So let's combine all terms here. So use the Leibniz rule here in combining all terms. So we have the final results here, 3 to the 8 minus t cubed sine squared cosine t minus t squared sine cube. So factor optional. So this is our final answer. Let's verify by computing I of t directly and differentiations. So verification by direct integrations here. So this is t to the 9, it is equal to t to the 9 over 3 minus t cube sine cube over 3. By differentiation here, we differentiate this. So 3 to the 8 minus t squared sine cube minus t cube sine squared cosine t. Okay, so we have the final answer here, 3 to the 8 t cube sine squared cosine t minus t squared sine cube. Then by using the Mathematica here, you have the given f of x squared times t cube, and a of t is equal to sine t. So we have b of t equal to t squared. Then a result here, Leibniz rule. So we have the you have the given here f a b and t as our variable. So we have the result here. So differentiate the integral of f of x from a of t. We have the given here a of t and b of t here. So simplify. We have the result here. So the same as this one by using the by using the by using the Mathematica here.